Thank you very much, Gil, and thank you for inviting me to this conference. It's very nice. I wish I could make it to the early morning sessions, but yeah, today was especially difficult because I had to prepare my talk last night. This is a work I did with Yimu Bao, a fantastic student at Berkeley, and Sunwon, who is a postdoc, a Miller postdoc, moving to MIT. And you can find it in this archive posting. So maybe since I heard it's just 20 minutes, I'll rush past that. Probably all of you know that there is a huge progress with quantum circuits that are becoming more controllable. There are many ways to make them now very beautiful. I want to treat them in this talk as new paradigms for quantum many-body physics. And maybe something interesting will also come out of that, but something interesting for applications. But I think there is something really new and exciting about them as many-body systems, many-body quantum systems. And one hint of that was in the discovery of the measurement-induced phase transition in hybrid quantum circuits. These are circuits which kind of give you the most, if you want, the quintessential quantum evolution. When we learn quantum mechanics, there's two types of evolutions we learn first, and they're both of pure states. Either you evolve the state unitarily with the Schrödinger equation, in this case, quantum gates, unitary gates, and the other is you measure projectively, and that also evolves the state through quantum collapse. So this is a circuit that is made only of these elements. So in principle, you can inject a mixed state, but if you inject a pure state, then it remains pure because it goes through the evolution by unitaries. It's pure. When it's projected to a pure state, and it's projected according to this usual Born law, basically that depends on the state. It has a Born law for probabilities. So this is the simplest setting, a pure state evolving, and what we get is like a tree of or an ensemble of many quantum trajectories of the state that are labeled by their measurement outcomes, a series of measurement outcomes. And in this thought experiment, what people did is they asked, what is the entanglement of this, entanglement entropy in this state per trajectory? If you measure in each trajectory and average, because if you have unitary dynamics by itself, it will give you volume law entanglement. If you measured everywhere, then of course you disentangled everywhere you have measured because you're measuring locally, and you will get area law or even non-entangled state. And what one finds is that there is a phase transition. Oops, something disappeared, but there is a phase transition at a critical measurement rate in which the wave function collapses, so to speak. So this quantum collapse from a highly entangled state to a low entanglement state occurs as a measurement, as a phase transition, and this can be understood through scrambling. If the unitary gates are sufficiently scrambling between measurements, then the measurements cannot reveal information on the quantum state, and therefore they don't collapse it completely, and you have a finite number, if you want, of logical qubits propagating through the circuit. Oops. So what I want to talk about in this talk is to treat this kind of hybrid quantum circuit as a generator of an ensemble of quantum states. As I said, right, it generates this ensemble of trajectories. And it's really important here, although we're in this in a conference on open systems, and this is an open system because we measure it, we can't describe this by a Lindblad equation. I'll discuss it later because we really want to look at the unraveling, if you want, of the Lindblad into trajectories. If we averaged over trajectories, if we traced over measurement results, then we would get basically a dephasing term, usually for most measurements, in the Lindblad equation, and we'll get nothing really interesting. The system will go to a steady state that is described like an infinite temperature maximally mixed state. So in this talk, I want to basically understand the properties of this ensemble of states that the circuit gives at its output. And we want to ask the question, first of all, how to characterize it theoretically, experimentally, and then if we know how to characterize it, can we define quantum phases of this special circuit ensemble, and how do they depend on some constraints of or architecture of this circuit, like the symmetries of the circuit. So what I'll show is that, interestingly, the pertinent properties of this ensemble, which is kind of strange and not unlike really equilibrium ensemble or a usual ground state ensemble, can nevertheless be mapped to studying the ground state of some effective Hamiltonian, albeit with an enlarged effective symmetry, not with the physical symmetry of the circuit. And that gives rise to new phases and phase transitions that you would not expect from a system of the same symmetry and the same dimensionality in equilibrium. So first of all, how to characterize this ensemble of trajectories? The first thing to ask is, can we characterize it by expectation value of observables? So that would mean taking some observable and averaging over, basically summing over all the possible trajectories, psi n are the unnormalized wave functions of trajectories, and then averaging over, if you have random gates, you can also average over the random gates at the end. What this gives you, if you average over all these things, is the trace over the averaged density matrix. The problem is, as I alluded to before, basically this gives you something like a dephasing channel. It's a unital quantum channel, gives you an average density matrix, which is just the unity. So at steady state, you don't expect anything interesting from this. The next best thing one can do is to consider fluctuations over trajectories in the ensemble. This is measured by higher moments of the expectation value in the states of the ensemble, such as this. This is the this is the kth example of the kth moment. So I measure the average over measurement results. This is PM, and then average over the random unitary gates. And in order to capture such moments, we need to somehow calculate the dynamics of n copies of the density matrix, basically n copies that propagate according to exactly the same unitary evolution and the same measurements. So not only the same measurements, the same measurement results occurring in this. So it's basically really n copies of your system. And this allows to capture such moments. By the way, purity and Renyi entropies are examples of these moments. So the first step I want to show you is that actually there is a neat way to map this kind of n-copy dynamics to an effective ground state problem. So the key is the following. First of all, since we have, let's look at the simplest case where we propagate two copies. So it's two copies of the density matrix. This is the initial density matrix. We start the dynamics. So we need to propagate the ket, the bra, the ket, the bra. So every unitary in our system and every measurement has to be replicated 4 times, right? 2 for the forward evolution, if you want, and 2 for the backward evolution of the bra. And this is how it looks in a network setting. In the end, depending on what we calculate at the end, the nice thing about this, whatever we calculate at the end can be inserted here. Because we folded the forward evolution, backward evolution, forward evolution, backward evolution, anything we calculate, and this example is calculation of purity. For example, it requires us to swap between the two copies and one side of the system and not swap in the other side. Okay, so we have we need to average over 4 unitaries, and if every unitary looks like a small unitary with a small angle coupling your qubits in this way, like a spin Hamiltonian, and averaging it is actually quite easy. And what you get is this, which looks like a short time of imaginary time evolution. Okay, so that will be key. That's provided this disorder or this randomness in the unitary is symmetric. Similarly, you can do the same for measurements, and if the measurement probability or rate is small, then again what you get is when you expand it, you see that you again get something that looks like imaginary time evolution over a small time delta t times some rate of measurement. So in the end, what you get is that this density matrix, this doubled density matrix, which I write kind of suggestively as a strange ket, is just propagated with an effective Hamiltonian acting in the Hilbert space of these 2 times 2 copies, right? 2 forward, 2 backward evolution branches. It acts as an effective Hamiltonian with imaginary time evolution. So this whole thing is mapped to imaginary time evolution. This unnormalized density matrix is evolved with linearly evolved with an imaginary time evolution. So it goes to a ground state in the end, after a long time evolution in a thermodynamically large system. Okay, so this is how it looks, and this is what, so we start with this initial density matrix, evolve it with imaginary time evolution. Now, what if we want to calculate some property of the circuit, some operator or some moment? As I said before, we wanted to look at such moments. Well, if we already have a replicated system, we just take this replicated moment and insert it here, and then we need to trace everything. Tracing turns out to be, you can implement the trace with this strange new Hilbert space using a bra that's basically this bra. It's a reference state that has some properties. If you cap this tensor network at the top with this bra, it basically implements the trace. So the moral here is that calculating circuit properties corresponds to calculating boundary matrix elements between the ground state of your system, if you're interested in the long time steady state, and some reference state I, and this is the normalization you get. And there is some subtlety that I won't get into about taking a proper replica limit here that we can discuss in questions. An example of an operator you might want to calculate, for example, is to calculate purity, for example, would be to calculate the swap operator over a region A. So in this case, that would be the swap operator, and the swap operator acts just like a normal operator on a space of 4 copies. It's okay. So now, what about the symmetries of the system? We're going to try to understand what phases are possible in this effective ground state, effective ensemble. So the first thing to understand is what are the symmetries. So first of all, there is a symmetry that's completely intrinsic to this dynamics and has nothing to do yet with what symmetries are imposed on the circuit itself. So I call it intrinsic dynamical symmetry. And it comes from the fact that the unitary gates and the measurements preserve the purity of the state. If you insert a pure state, it remains pure. Because of that, there's symmetry to permutations between only the kets of your system and separately between only the bras of your doubled or replicated density matrix that's evolving in time. So you see, you can, because the dynamics does not mix or does not couple forward and backward branches, it allows this kind of permutation, independent permutation. By the way, if I applied some mixing term, some dephasing, you know how it comes in the Lindblad terms, it comes as coupling between the two branches, between the ket and the bra branch. That would break this independent permutation symmetry of only the kets or only the bras. Okay, so that would break this symmetry. There is another symmetry that I won't talk about much here, but it's there due to the fact that your dynamics conserves the hermiticity of the density matrix, and that's this Z2 hermiticity symmetry. It's actually anti-unitary, if we want to be careful. It acts sort of like an effective time reversal symmetry here. And yeah, so an example of where this symmetry Sn cross Sn is important is the measurement-induced transition. Actually, the breaking of this spontaneous breaking of this symmetry gives rise to a volume law phase. And you can see that simply in the case of Z2, where this breaking of Z2, if I swap one side of my top of my system and not swap the other, the symmetry is between swap and no swap. And having swapped one side and not swapped the other side, if I have a spontaneously broken symmetry, then it forces a domain wall with length L to go through my system, and that costs a volume law, basically linear free energy. So the entanglement entropy is volume law in phases where there is a spontaneously broken symmetry, Sn symmetry. In addition to that, we can, of course, also add physical symmetries to the circuit elements. So here we have these, n copies of the circuit, actually 2n copies of the circuit, because of forward and backward. Each one has this, say, symmetry, internal symmetry G. And it has to be properly combined with this Sn cross Sn symmetry, and that leads to this enlarged symmetry. Okay, so the Hamiltonian we will derive will have to have this enlarged symmetry if the physical circuit is constrained by the symmetry G. Okay, we'll see examples where it's kind of not so intimidating. This looks like a huge intimidating symmetry. But the idea is that the phases of the circuit ensemble now correspond to ground states of an effective Hamiltonian with not symmetry G, but some larger symmetry that can support a richer phase structure than we would expect just based on the symmetry of the circuit. And I'll show examples where we get surprisingly phases we would not expect to have in a circuit with the same symmetry. So the simplest case that I want to give first is a qubit circuit with a circuit of qubits with Z2 symmetry. So the symmetry generator is a product of all the Z's. Here are all the possible circuit elements if they're kind of nearest neighbors. Single side gates with Z are allowed, and ZZ and ZZZ are allowed, but X you're only allowed only allowed even number of X's so that you preserve the Z2 symmetry. You can also measure one Z gate, one Z qubit. You can measure Z on one qubit. You need to measure XX on 2 qubits. And if you play the game that I just showed you, you get that the enlarged symmetry is D4 cross D4, but it turns out that in this case, it's sufficient to consider just one D4. There is another special symmetry here that I didn't mention that kind of reduces the effective symmetry to just D4. So now you classify your states according to this D4 symmetry, which is basically the symmetry of the square. These are the two Z2s, and this is the S2 permutation symmetry. And that implies 4 different area law phases, 6 volume law phases, and actually a topological area law phase that's protected by a combination of Z2 cross the S2 symmetry, which so far I have to say we haven't seen, and we're interested whether it can in principle be realized or there is some obstruction. But already these 6 volume law phases are quite interesting and seemingly unexpected, so let's see if we can get them. So before we get them, let's try to understand a much simpler problem that was Yeah. Yeah. Okay, so yeah, I'll finish in 2 slides. I'll finish this, and I won't talk about fermions. I'll just advertise Yimu Bao's talk on fermions. So maybe just 2 slides. Okay, so as a warm-up exercise, this is Tim Shi and Sang looked at this exercise where you have a circuit of qubits, and the only thing you do is measure it, and you measure according to these rules that conserve the Z2 symmetry. So you measure only Z or XX. If the Z measurements dominate, then you get a random definite parity state in each trajectory. Basically, you measure Z, you collapse the system to spins in the Z direction, more or less, plus fluctuations, but this can be can be checked by looking at the variance of the parity over a subsystem of length of some length A, and increasing that length and seeing that it goes to some constant, the variance of the parity. If that's true, then this is volume, and then this is a phase. The other phase is if you dominate with XX measurements. In this case, you want to collapse the state into X direction, but you'll get basically random X direction. So how do you measure this order? You can't measure it by just the usual XX correlation function. You need to look at the Edwards-Anderson order parameter correlations. Basically, you look at the moment XX squared averaged over the ensemble. And that is non-zero or non-decaying in that phase. And these are indeed the two phases you find. Okay, so in this case, basically, it's exactly what we would expect with a system with Z2 symmetry. There is no signature of the enlarged symmetry in this case. So here is just my last, well, before the conclusions. So here is a more involved model which has both unitary and measurements, but it's actually quite simple. It has two chains. The chain 1 just has only unitary, unrestricted by symmetry evolution. So this only has unitary evolution, chain 1. Chain 2 has only measurements, exactly like the measurements I told you before, either ZZ or either on-site Z measurements or two-site XX measurements. So if we don't couple these, chain 1 is in a volume law phase, of course, because it just has random unitary dynamics. Chain 2 has an area law phase with either volume law, with either breaking or not breaking symmetry. And now the question, what happens when you couple them? Now, because each phase is a gap, each one of those is a gapped phase in terms of this effective Hamiltonian. One is a gapped Ising ferromagnet, the other is a gapped, is also a gapped phase that can be understood also as some kind of Ising gapped phase. So when you turn on a coupling between them, they survive. However, the critical point does not have to survive. And there is a new phase that opens between them. And here you see that now these two order parameters, the Edwards-Anderson order parameter and this string order parameter that measures the parity variance, measures how much you conserve parity, basically, that in a Z2 circuit would be dual to each other and have to meet at the same point, like here, like we had here. They don't meet anymore at the same point, and there is a phase, a third phase, which has neither the parity order or the Edwards-Anderson, parity string order. This was what we called before the paramagnetic phase. The Edwards-Anderson order is the ordered phase, and there is now kind of a featureless phase which has neither one when you couple them. And needless to say, all of these phases are volume law because of the unitary dynamics in chain 1. I didn't show the entanglement entropy, but it's volume law throughout. So you have a one-dimensional system with volume law entropy that supports two different kind of, if you want, ordered quantum ordered phases, plus a featureless phase, which maybe is related to the finite temperature thermal phase. So this is, first of all, not what you would expect from a Z2 circuit in equilibrium, and there is more phases than you could classify with just a Z2 symmetry. Okay, yeah, I'm done. So this part I'll skip, and I'll get to my summary. So I talked about phases of quantum circuits, and that they can be classified as ground states of an effective Hamiltonian with an enlarged symmetry. I talked about the qubit circuit. I didn't talk about the Gaussian fermion circuit. I invite you to Imu Bao's talk in the student talks. He'll talk about this, plus some new results in this. But the upshot is that in this case, in the qubit circuit, we saw that Z2 symmetry was enlarged to D4 and allowed more phases. In the Gaussian fermion circuit, we start with a circuit with only Z2 fermion parity, no U1 symmetry. It's enlarged to U1, and because of that, it allows a critical phase, a U1 critical phase with log L and log of the volume entanglement in one dimension. And it shows, we see evidence for a Kosterlitz-Thouless transition into two area law phases, one topological and another trivial area law phase. So maybe I'll just flash the questions in Outlook to let people some time to ask questions.